Newtonian versus Einsteinian gravity. What's the difference? Imagine a universe where gravity is just a simple force pulling objects together. Now picture a universe where gravity is a bend in the fabric of space and time. These are two very different ways scientists have understood how gravity works. Let's explore how these ideas changed our view of the universe and what makes them unique. Back in the 17th century, Isaac Newton proposed that gravity was a force acting at a distance. He said every object with mass pulls on every other object with a force proportional to their masses. The farther apart they are, the weaker the pull, following a rule called the inverse square law. Newton believed this force acted instantly across space. So, if the sun suddenly disappeared, Earth would stop orbiting immediately. Newton's ideas explained how planets move and why objects fall on Earth. He saw space and time as absolute, fixed backgrounds where gravity was just a force pulling objects together. Fast forward to the early 20th century, and Albert Einstein introduced a new way of thinking. He said gravity is not a force but the result of the curvature of a four-dimensional fabric called space-time. Massive objects like the sun cause this fabric to bend. When planets orbit the sun, they are actually moving along the shortest paths within this curved space-time. Einstein's theory also says that changes in gravity travel at the speed of light, not instantly. So, if the sun vanished, Earth would keep orbiting for about 8.5 minutes before feeling the change. This is because it takes that long for the gravitational effects to reach Earth at the speed of light. Another big difference is what causes gravity. Newton thought it was just mass. Einstein showed that energy, including light and heat, also influences the curvature of spacetime. This explains phenomena Newton's laws couldn't, like the precise precession of Mercury's orbit. Mercury's orbit shifts slightly each time it completes a cycle, tracing a rosette shape rather than a perfect ellipse, which Einstein's theory accurately predicts. Newton's equations are simple and still useful for everyday tasks, like calculating the path of a spacecraft or engineering projects, where extreme precision isn't needed. Einstein's theory is essential when dealing with very strong gravity, such as near black holes, or when high accuracy is required, like in GPS satellite systems. These satellites need Einstein's corrections to give precise location data because they orbit high above Earth, where gravity's effects are slightly different. So, in simple terms, Newton saw gravity as an instantaneous force between masses in a fixed space and time. Einstein saw it as the warping of spacetime caused by energy and mass, with effects that travel at the speed of light. This shift in understanding marked a major milestone in science, transforming how we see the universe from a static stage to a dynamic, interconnected fabric shaped by matter and energy.